you can have a magnetic field as x, and you can have current as y, and you can have force as z.
How can you tell on a two-dimension the z?
X's mean
Away.
z away, dots mean z towards.
Okay.
And again, everything in this class, everything's going to be perfectly perpendicular. You will not have any goofy angles. I can't guarantee that's going to be the case when you get to college. They might throw some sines and cosines at you, but in this class it's all perpendicular. Okay, so our options are up or down. So if you think it's up, raise your hand. If you think it's down, raise your hand.
Isn't it down?
See, most of you seem to think it's up. Let's see. So we have a magnetic field that is what? Away from the plane. Magnetic field is into the plane, and current is to the right. So our force would be blue. Our force is up.
Oh, with my left hand. Dummy.
Did I put the answer in? Let's see. I did. Look at that. Next, take a look. Now you got a Z magnetic field and a Y force. You're gonna have to come up with an X current.
Or are we doing this on a test?
Oh, absolutely. Yeah, you should. They should sell tickets to the IEEE test. I remember when I took my engineering physics courses at Oregon State. We're all going.
Wait, give me a second. What if we just do this on the whole test the whole time?
Yeah, you will be like, okay, and you should. It's like, and it's a really good device. You totally should. Don't be like, I'm embarrassed to show my people. Like, seriously, like imagine a lecture hall full of 300 engineering students, and we're all going.
It's better than Einstein. I just went like this. I was like, my arm doesn't work like that. I got a brace.
Okay, so if you think you got a left force, raise your hand. And you got a right force, raise your hand. See, most of you think it's a left force? It's a left force. Sorry, left current. You know what I'm talking about, left current. Okay, here's another one. Our magnetic field is now still Z, but it's now coming out of the plane.
It's going down.
We got an X current, so we're going to go up with the Y force. Do you think it's a down force? Raise your hand. Up force, raise your hand. All right, down force. Now again, in these examples, I made the magnetic field the Z in every case, but the magnetic field does not need to be Z. So it could be anything. For instance, in my example here, I made the magnetic field X and my current Y, so my force would be Z. So if I make a magnetic field X and my current Y, now my force would be into the plane. So I have a force X, that would be FB. Does that make sense? So magnetic field is to the right, current is up, and the force would be into the plane. Okay. Is this rattling around? You got this? All right, how much time we got? We got 10 minutes. Okay. Particles. Oh, this is great. When particles travel into a magnetic field, they feel a force. Okay? So if I send a positively charged particle into this magnetic field, it's going to feel a force. If I send a positively charged particle into this magnetic field, it's going to feel a force. Let's take a look. What direction will this positive particle, in what direction will it feel a force? So use your right hand rule and figure out, just make it easy, we're going to use protons and electrons to make it easy. But it could be any positive charge and any negative charge. So I'm going to get my force pen ready to go.
Mr. Byers,
Yeah.
The different X's and dots are they positive or negative?
No. Into the plane, out of the plane. Into the plane magnetic field, out of the plane magnetic field.
So how does the particle change that? Or why does it?
Okay, so you have a Q traveling in a V into a B, so it's going to feel a force. So in both cases, you have a charged particle Q traveling with a velocity V that's not given, and it's going to feel a force B. which is, yeah, the math is next. Okay, so with this one, you've got a Z magnetic field, you've got an X velocity, your force is going to be what? Y, it's going to be up or down. So, magnetic field, in, velocity, it is positive, velocity this way, so it's going to feel a force that is going to be up, Fv. And the electron would be the opposite direction, because the electron makes basically opposites everything. The electron's going to be the opposite direction. And then the proton, it should make sense, if you invert the magnetic field with an into the plane, it's going to be up. With an out of the plane, it's going to be down, Fb. And for the electron, it's going to be the exact opposite. It's going to be Fb.
So how are you using the right-hand rule to begin with?
Okay, so get my right-hand rule.
Yeah.
And with this magnetic field, it is into the plane.
Right.
So I'm aiming my fingers into the plane. My current or velocity, which is my finger, is pointing to the right. So my force is pointing up.
So you know it's pointing to the right because of the green thing there?
Yeah, because of the arrow.
Yes.
It's going this way.
Yeah, I couldn't tell it.
Oh, yeah, because you're sitting in the back. There's glare. Sorry.
I thought it was just a line.
Maybe one of these days I'll get a better projector, but until we got that, yeah, sorry. It's going that way. It is entering the magnetic field, if you will. Okay, does that make sense what's going on?
Yep.
Now my question for you is this, and it's going to take you a couple seconds to think about it. The motion of the proton, as it enters the magnetic field, it's going to get pushed, right? And it's going to get pushed a number of ways. Is it going to get pushed linearly and travel like that? Is it going to get pushed in a parabola and travel like that? Or is it going to get pushed in a circle and travel like that? So this is going to be line, circle, parabola. So talk with your neighbor. What are you going to get? Are you going to get a parabola? Are you going to get a line? Or are you going to get a circle?